Okay. Well, good morning, everyone. I'm Nicholas Achilleos from UCL, University College London. I'm a lecturer in physics. I'm part of the astrophysics group, and we in turn are part of the Department of Physics and Astronomy. I'm a member of the Cassini magnetometer team who study the magnetic field of Saturn, and I'm also a co-investigator for the proposed magnetometer instrument on the Jupiter Icy Moons Explorer mission, or JUICE, which is scheduled for launch in about 2022, I think, or thereabouts. So my background is the gas giant planets, and I've also got an earlier background in astrophysics as well. Okay, so what I wanted to talk to you about today is seasonal influence on current sheet structure at Saturn, because I thought at the same time this was a good example of how seasonal effects influence magnetospheric structure of a giant planet. And also there's a nice link to the planetary magnetospheres lectures that I'll be giving next week. So before we go into the diagram of Saturn's magnetosphere here, on the right is sort of a breakdown of what I'll be talking about. We'll be looking at aspects of the magnetosphere-solar wind interaction, how that influences the geometric shape of the current sheet, and how that's related to the response of that structure to the attack angle or the direction of the solar wind with respect to the planetary dipole. And just to emphasize that I'll touch on many concepts here that we'll return to in more detail next week in the planetary magnetospheres lectures. Okay? All right, so to start off with, let's have a look at this diagram provided by Emma Bunce of Saturn's magnetosphere. And what we see here is sort of the classical picture of a magnetosphere, which is essentially, as I'm sure you all know, a cavity carved out in the solar wind due to the deflection of the solar wind charged particles by a planet's magnetic field or magnetospheric field. So in this diagram here, the particular feature of interest that I want to draw your attention to, this is Saturn in the middle of the diagram here, and it's surrounded by a disk of plasma. And this disk is confined generally towards the equatorial regions of the system. So a useful image that I always keep in mind is that the magnetic field lines, which are these white curves here, you can think of as like a wire framework that's very rapidly rotating. You can think of cold ions as beads that move on these wires. And so when you spin a wire framework up, the beads tend to congregate towards the centrifugal equator, and that's essentially what's happening in this system to give you this rotating magnetized disk of relatively cold plasma. So the ultimate source that feeds these disks are moons. So at Jupiter you've got the volcanic moon Io, that's the source of mass, and at Saturn you've got the icy moon Enceladus, which is the principal internal source of mass for this disk-like magnetosphere. Okay, so here's a picture. On the left here, we've got a false color image of the famous water plume that erupts from Enceladus' southern hemisphere through essentially cracks in the ice sheet. And this is the principal source of mass, something like tens to hundreds of kilograms of mainly water group ions per second are added to Saturn's magnetosphere. A hint of this source was first discovered by the magnetometer instrument, which detected a characteristic deflection of the magnetic field during the first Cassini flyby of Enceladus. And then on subsequent closer flybys, it became very obvious what was happening. On the right here, we've got Io, whose face kind of looks like a pizza that's dotted with all these volcanoes. And here, in absolute terms, the mass source is stronger, of the order of 1,000 kilograms or so per second of sulfur and oxygen ions per second added to the system there. For the Earth's magnetosphere, of course, we don't have the equivalent of an active moon like this that can act as an internal source. And for the giant planets, the combination of the large magnetospheric size and the rapid rotation gives us these magnetodisk structures. Okay. So what about observations? What can observations tell us about these magnetodisk structures and the kind of processes that are shaping them? A good starting point here is if we look at magnetic field data from the insertion orbit of Galileo at Jupiter. This is way back in September 95 or so, if memory serves. And the spacecraft remained very close to Jupiter's rotational equator throughout this pass. What we're seeing here in the panels is the radial, meridional, and azimuthal field components in the famous spherical polar coordinate system. And what we see many things, but one of the obvious things that we see is that the radial and the azimuthal components are changing periodically. There's an algebraic change in sign of those field components, and the two field components, as you can see, are very clearly changing more or less in antiphase with each other. Maximum in one component corresponds to minimum in the other, and as I mentioned, those changes are happening periodically at a period pretty close to the planet's rotational period. Okay? So a simple hypothesis that one can formulate to try and explain observations like this is that it might come about from the effect, if you can look at this diagram here, of a spacecraft sitting near the rotational equator, subject to the changing magnetic field that one would see from a magnetic axis, the purple arrow here, which in Jupiter's case is tilted at about 10 degrees to the rotational axis. So if we think of the magnetodisk as a simple planar wobbling plate, this means that the rotation of the planet places the spacecraft alternately above and below the magnetic equator. In other words, alternatively in regions where radial field is positive and negative. So that's a nice simple picture that we can start off with to try and explain what we see. In reality, though, we need something additional, and one of the principal reasons for that is illustrated here, where we've plotted on top of the data the prediction for the field that one would see just due to the rotating internal dipole of the planet alone. So you can see that the amplitude in the field is weak compared to the observations. The model waveform is sine-like compared to the sort of square wave signatures that we see. And the phase relations are also very different. If you look at the wobbling dipole model, for example, I've placed a vertical line here, which is near a minimum in the radial field, and at the same time close to a positive going zero crossing of the azimuthal field. So the model predicts that those two components should be sort of a quarter of a cycle out of phase. The observations, as we saw before, show that the two components are something like 180 degrees or half a cycle out of phase. So the phase relations are different. So what's going on? We need some other source of field perhaps to give us a better explanation of what we're seeing. An improved model comes from, for example, this paper by Cowley et al., who analysed magnetic field data from the Ulysses-Jupiter encounter, and they were able to interpret a lot of the observations they studied from a field model that's illustrated in this rather scary-looking diagram here. And the lines in the background of this diagram illustrate the kind of field structure that you need to best explain the observations. Here's the planet, which is the unit disk at the origin here. Close to the planet, you have the nice loop-like structures of a dipole field. As you come out further along the equatorial plane, you can see the field lines pinched very strongly in the radial direction, forming this disc-like or tail-like shape. Okay, so this diagram is in the frame of reference which is anchored to the tilted rotating dipole, which means that the wobble of the dipole is now transferred to the spacecraft trajectory, which is this curve here that passes through the diagram. And so this is a nice representation because it shows us that in the case of Ulysses, and certainly in the case of Galileo, the spacecraft makes these periodic dips into the center of the current sheet, current that needs to flow there to support this stretched dipolar field that we see. Okay, so that current sheet has to support current flow in the sense of planetary rotation because of the polarity of Jupiter itself. And that means ions flowing in the sense of planetary rotation, electrons drifting in the opposite direction. So those particle drifts are an important contribution to that magnetodisk current, but certainly not the only contribution. Further work by Kivelson and Karana showed that they looked at Voyager data and they did a very careful analysis of the phase relations of different field models, and they concluded that to get even better agreement with the observations, you need a field structure which has what's called true bend back of field lines. So in reality, what we have is a field lines that don't lie in one single flat plane, but that plane of the field line, if you will, curves and bends back against the direction of planetary rotation. The further out one goes in the magnetosphere. And that effect is associated with strong outflow of plasma from the Io torus, and a similar effect is seen at Saturn as well. Okay, so speaking of Saturn, here are magnetic field observations for Cassini. And this is essentially the analog of the Galileo observations that I showed, and there's some interesting differences here. So let's have a look. So what we have here is the radial and the north-south field component from the Rev 3 orbit of Cassini, February 2005. And you can see that this is a cylindrical components, and you can see that the outer magnetospheric region, which is here and over here during this pass, has a radial field which is persistently, on average, persistently negative. So rather than the nice symmetric change in sign that we saw in the Galileo data, now we're seeing something quite different. We're seeing a field component with a persistently constant algebraic sign. So that's one point of departure. Like the Galileo data, the Cassini data do show these periodic disturbances, but this is kind of weird in the case of Saturn because the internal dipole of Saturn and its rotation axis are almost exactly parallel. Okay? Now, we're going to be talking in more detail about what imposes that periodicity at Saturn next week, but it's a very different thing from a rotating tilted dipole. Okay? So that persistence in the sign of the field component here, the radial field component, implies something interesting about current sheet location, and you've probably already guessed is that implication is that the magnetodisk is not symmetric about the rotational equator. It can't be, otherwise we'd retrieve that nice positive-negative pattern, and we clearly don't see that. So the implication here is that we are consistently on one side of the magnetic equator throughout this pass. Okay, so another thing we can do is we can divide the field components by the total field strength, and this gives us an idea of how dominant they are in different regions of the magnetosphere. Okay? When we do this, we see quite clearly that we can separate the magnetosphere into two different regions. This shaded region here is within about 15 Saturn radii of the center of the planet, and you can see if you look at the field component ratios that it's the north-south component here that has a magnitude close to 1 and is dominant in that part. And in this is the quasi-dipolar region, and then in the outer magnetosphere, or the so-called current sheet region, it's BR over B total that dominates. Okay, so there's quite a clear separation there between the two. So we see lots of other structure, of course. We see these strong dropouts in the field associated with flapping or sporadic encounters with the current sheet, and also this 10.7 hour or thereabouts oscillation, known in the community as the rotational anomaly or the camshaft signal. Okay, so the period, as I mentioned, is the subject of much ongoing Saturn literature or research, and recent observations from Cassini have shown that actually that periodicity consists of two distinct periods, each dominant in a different hemisphere of the planet. So it's quite a mysterious story, and we'll come back to that next week. But for present purposes, we noted that the Saturn observations indicate that if you're in the rotational equator of the planet, you are persistently below the center of the current sheet in this case, and this is a nice illustration of the kind of current sheet configuration that you need from Araj et al. 2011. So the idea here is solar wind is blowing in from the right. Here's the schematic magnetopause. The magnetic dipole of the planet is tilted with respect to the orthogonal to the solar wind direction, and the force balance in the system requires the current sheet to adopt this bowl-like shape. So at the time of the observations that I showed, the angle between Saturn's north magnetic pole and the upstream solar wind direction was something like 70 degrees. In other words, the southern hemisphere was experiencing its summer solstice. That angle, of course, changes during Saturn's orbit, and we'll see the effects of that in just a moment. The equivalent angle for Jupiter varies symmetrically according to its rotation period because of Jupiter's dipole tilt with respect to its rotation axis. But for this solar wind dipole angle to change significantly at Saturn, we require orbital periods to pass, 30 years approximately. Okay, so the idea is that this effect at Saturn leads to a transmitted asymmetry in magnetic pressure on the top and bottom of a planar current sheet, which causes it to adopt this bowl-like shape. This is consistent with MHD simulations of the planet's magnetosphere, such as those shown here by Hansen et al. Okay, so at UCL we have a relatively simple, compared to MHD simulations, magnetodisk model, and a sort of a brief history of the model is shown here. Basically what we did is we adopted Gerard Caudal's model formalism for the Jovian magnetodisk, and we adapted it for the case of Saturn using Cassini data to construct our boundary conditions. And on the top panel here, the color scale shows you the shape of magnetic field lines for the model. So you're looking at a single magnetic meridian of this axisymmetric model. And the purple curves here are contours of constant field ratio, B radial over B total. And in this case here, this is an equinox configuration. So solar wind is coming in exactly along the plane of symmetry of the system between the north and the south, the equatorial plane. And the fringing field associated with the magnetopause currents is very simplified in this model. It's simply a southward pointing uniform field throughout the modeled region. But although we sacrifice a bit of realism, we can use that kind of formalism to think about how things change if we go to a solstice configuration. So in the solstice configuration, solar wind is now blowing from this direction below the rotational equator of the planet. We can stick in a fringing field that's tilted to try and simulate in a simple way what one would expect. And in this case, we intensified that fringing field as well as changed its direction. And then as the calculation proceeds, you do see the field lines tilt away from the rotational equator as you come into the outer magnetosphere. And here's a comparison, I don't know if you can see it, with the yellow dashed curve, which is the empirical bowl-shaped model of Arridge et al., who used observed encounters with the current sheet to constrain that geometrical shape. So the agreement is reasonably good, but we would like to sort of, build in a more sophisticated treatment of the fringing field. But the message is here that information about the solar wind direction is carried by the magnetopause currents and then how they consequently affect the interior field of the system. The bottom panel is contours of constant magnetic pressure. The magnetic pressure at the center of the current sheet is a local minimum because of the force balance condition. Plasma pressure at the center of this disk is a maximum. So magnetic pressure to balance the total pressure must be a minimum. We'll return to that theme next week again. And you can see that these white contours of constant magnetic pressure show you that the local minimum, the center of the current sheet, does rise out of the rotational equator as you come into the outer magnetosphere. What we can also do using this kind of a modelling approach is to ask the question, what would happen if we placed a planar equinox disk into a system which had a solstice type solar wind direction. So the bottom panel here essentially summarizes the results of answering that question. And what we show here is a perturbation angle between the magnetopause fringing field associated with that solstice solar wind direction and an equinox disk field. So in the south, that angle is small. which means that the disturbance is or the perturbation is a compressional one, which tends to increase magnetic pressure. In the northern part of the system now, that angle is quite large, values around 90, 100 or so, which tells us that here the perturbation is more of a rotation than a compression, so it doesn't affect the magnetic pressure so much. That leads to an asymmetry in magnetic pressure in the north and the south, so-called lobes of the current sheet. So the bottom line here is that if you try to maintain a planar disk under solstice, solar wind, attack angle, you can't do it because this asymmetry in the magnetic pressure will force the structure to adopt that bowl-like shape. Okay, you can also do interesting experiments like take vertical cuts through your disk model, and this is what we've done here at a radial distance of 19.4 R Saturn, and we show profiles with respect to the vertical coordinate Z equals 0 corresponding to rotational equator. The red and blue curves are the hot and cold plasma pressures, and the purple curve is magnetic pressure. So this is a nice equinox configuration, magnetic pressure and the plasma pressure changing in an anti-correlated way, which reflects the force balance in the vertical direction. Here we have our solstice disk, and because the disk is now asymmetric with respect to the rotational equator, so too are the pressure profiles. However, if you stick with the solstice disk model and now make your model cut in a direction locally perpendicular to the current sheet plane, you retrieve some kind of symmetry in the profiles, as you would expect, because force balance dictates that in a direction locally orthogonal to the current sheet, you maintain force balance in that direction. Okay, so now we can come back to observations. Before we saw solstice, southern summer solstice observations for Saturn. Here we see observations for 3 orbits during the period late October to early December 2009, which was the equinox year at Saturn. And we have the radial and the total field in the top 2 panels. And you can see, I hope, that you have a very different kind of observation, now more in line with the Galileo observation, showing you a nice symmetric positive-negative variation in the radial field. Very different to the solstice observations. So during this period, that dipole solar wind angle, which is what controls what we see here, was less than 2 degrees from the orthogonal configuration, and so we would expect an equinox disk to be a good representation of the system. And indeed, these algebraic changes in sign of the radial field show us that the mean position of the current sheet is now much closer to the planet's rotational equator than it was during the summer solstice. Okay, so to summarize, the current sheet at the giant planets, and indeed all magnetized planets, is an important region in the magnetosphere. It's a structure which at Jupiter and Saturn in particular plays a central role in plasma transport and mass loss. Again, we'll be coming back to that next week. The balance of forces means that centrifugal force plays an important role confining cold plasma towards the equatorial region, but sheet structure is also affected by the external solar wind driver, and for this particular presentation, its angle of attack with respect to the magnetopause of the system. Information about that attack angle is transmitted into the interior of the system by the fringing field associated with magnetopause currents, and at Saturn in particular, as we've seen, this gives us at solstice the bowl-like rather than the planar disk configuration for the current sheet. Similar effect at Earth has recently been modelled and described by Sigonenko. Thank you.